Hey everyone, welcome back to the channel Code with AKJ. Today is day 28 of solving LeetCode 75 challenge series. And if you are new here, make sure to subscribe and hit that notification bell so that you don't miss any update. Today we are solving a very interesting problem, Dota2 Senate from LeetCode, which involves game theory, queue, and greedy strategy. So by the end of this video, you'll understand both the brute force and optimal approaches with both time and space complexity analysis. So let's quickly dive in. So the problem statement says in the world of Dota 2, there are two parties, the Radiant and the Dire. The Dota 2 Senate consists of senators coming from two parties. Now the Senate wants to decide on a change in the Dota 2 game, and the voting for this change is a round-based procedure. So for in each round, each senator can exercise one of the two rights. So the two rights here are ban on one senator's right, that is, a senator can make another senator lose all the rights in this and all the following rounds. And second right here is to announce the victory. That is, if this senator found the senators who still have the rights to vote and all are from the same party, he can announce the victory and decide on the change in the game. So we are given a string senate representing each senator's party belonging. The character R and D, that is R represents Radiant party, D represents Dire party. Then if there are n senators, the size of the given string will be n. So the round-based procedure starts from the first senator to the last senator in the given order. This procedure will last until the end of voting. All the senators who have lost their rights will be skipped during the procedure. So every senator is smart enough and will play the best strategy for his own property. Predict which party will finally announce the victory and change the Dota 2 game. So the output should be Radiant or Dire. So this was our problem statement. So let's quickly understand this problem statement. So in the world of Dota 2, there are two parties, that is Radiant R and Dire D. So the Senate consists of senators from both parties, R and D, who vote in rounds. So it's a round-based procedure. So each senator can either ban one opponent senator rights, making them unable to vote, and also announce victory if only their party remains. So this would be the two rights each senator can exercise in each round. So we are given a string senate representing the sequence of senators. We need to predict which party will win if every senator plays optimally. That is, every senator is smart enough and will want to win their party by choosing the best strategy for their own party. So we need to predict which party will finally announce the victory by exercising these two rights. So let's quickly go through these two examples and understand this problem more clearly and come up with a brute force approach, and then we'll later on try to optimize this approach and we'll finally move on with our time and space complexity analysis. So in example 1, we have given a string RD. So the first senator comes from Radiant, that is R, and he can just ban the next senator's right in round 1 itself. So after exercising this first strategy, the second senator can't exercise any rights because the first Radiant R has banned him in that particular round. So in round 2, the first senator can just announce the victory since he's the only one guy in the Senate who can vote. So in this way, the person who comes first, that is the Radiant R, he just quickly exercises the first right, that is banning the other's party right, that is Dire D. Finally, he was the only one in the second round who can vote, so he can quickly announce the victory as he is the only one who can vote. So in our example 1, the output would be Radiant. And in our example 2, so the first senator comes from Radiant R, that is R, and he can just ban the next senator's right in round 1, that is the person at the index 1, D. In the second round, as the second senator, that is the D, can't exercise any rights, and the third senator that comes from Dire D, and he can ban the first senator's right in round 1, that is R. So finally in round 2, the both first index and second index senators has been banned from voting. So in round 2, the only person who has remained and who can vote is the person from the party Dire. So he's the only one remaining in the round 2. So he can announce the victory as he's the only one guy in the Senate who can vote. So in our example 2, the party who won the voting is Dire. So we'll return Dire. So this would be the explanation of both examples, example 1 and 2. So let's quickly come up with a brute force approach. So in our brute force approach, we'll remove banned senators manually in each round. So our algorithm says we'll iterate through the Senate string. So if an R senate appears first, we'll ban the first D senator after them. And if a D senator appears first, then we'll ban the first R senator after them. We'll try to repeat this process until all remaining senators belongs to one party. So this would be our brute force approach. So until or unless a single party members remains in our given string, we'll try to ban the other party's senators one by one manually, and finally we'll return that party's value, that is either radiant or dire. So let's understand our brute force approach by quickly dry running few examples. So how our brute force approach works, and then we'll try to code that brute force approach. So in our brute force approach, we'll take a vector of bool where we'll track the senators who have been banned. So for this given example, so the vector contains two values, and initially both have values false, that is they both have the right to vote initially, and we'll iterate through our senator string, that is initially our senator's party would be from party radiant, that is R. So R exercises his first right, that is to ban the next senator. So he bans the next senator, that is from the party D. So we'll mark this particular party D as true in our vector. So the vector contains false and then true. So from the first round, we can say that the party D has no right to vote as he's been banned by the first party radiant R. So in our second round, before moving on to the second round, so in our second round, since the only one radiant R has the right to vote, we'll return radiant as an answer. So let's quickly dry run this example as well. So initially everyone has the right to vote. We'll iterate over our string senate. So the first character would be R. So he tries to ban his next opponent, that is from the next party, that is D. So let's say he bans this particular senate D presented this particular index 1. So the vector becomes false, true and false. And when we go to the next index, that is this particular index 1, as we can see that he has been banned from voting, so we'll skip this index and we'll move on to the next index. So this, since this particular D has the right to vote, he'll try to ban his opponent party, that is R. So the vector becomes true, true and false. So in first round the vector becomes true, true and false, that is these two senators has been banned from voting. So this was the data from round 1. So coming to the second round, we'll check the vector data, that is true, true, false, and since this particular D value has only the right to vote, so he'll use his second right, that is to announce the victory, as he's the only one to vote. The answer would be dire. Let's quickly move on to the code of our brute force approach, and let's quickly submit and let's see whether it gets accepted or not, and we'll determine its time complexity and space complexity. So here's the code for our brute force approach. Here I've taken the while loop and it runs until or unless any of this condition fails. So here I have also taken two variables, radiant has vote or not and dire has vote or not. I have also taken the vector of bool of banned, which would be initially false, as each and every senator has the right to vote in the beginning of the round. So here I have used for loop to iterate over our senator string. So the first step here would be to check if the current senator has been banned from voting or not. If he is being banned, we'll skip that senator and we'll move on to the next index. So if the current senator is from the radiant party, that is R, we'll initialize radiant has vote with true and we'll try to search for the first available D and we'll make him banned by making the banned vector of J to true and we'll break from that loop. When we move on to the next index, we'll again try to find these three steps, whether the current character is being banned or not. So if it is banned, we'll move on to the next index and then we'll check whether he is from the radiant party or from dire party. So if he is from radiant party, then we'll try to search the dire senator, the first available dire senator, by again using a for loop to ban him. Or if the current senate is from dire party, then we'll assign his vote and we'll again check for the first available R senator, that is from opposite radiant senator, using the for loop, and again we'll try to ban him by making the band of J as true and we'll break from that loop. So after every round we'll try to check from the given vector, that is this particular radiant has a vote or not. So if he does not has vote, it means the dire has that vote after finishing that round. Then we'll return dire. If dire has vote variable is false, it means the senator string has all the radiant senators who has the right to vote and they can announce the victory. So we'll return radiant. So in this way, using the while loop, which runs until or unless it breaks any of this particular condition, we'll return our answer as radiant or dire. So let's quickly submit this code. As you can see, this approach gives us time limit exceeded because of its worst time complexity, that is O of n square. It would take n times, and for every senate we are using a for loop to find another senator which also takes n times. So the overall time complexity becomes O of n square. And coming to the space complexity here, it would be O of n, as we are using a external data structure banned vector which helps us to track the particular senate has been banned from voting or not. So in this way, our brute force approach works. Worst time complexity, that is O of n square, and space complexity is O of n, which is too slow for larger inputs when the n becomes more than 10 power 4. So let's quickly analyze the problem statement well, and then we'll come up with an optimal solution. So another data structure which would help us optimally calculate the results. So before moving on to our optimal approach, let's understand why our brute force approach didn't work, what are its drawbacks, and what we can learn from it and try to optimize it in our optimal approach. So in our brute force approach, we have iterated through our entire list for each and every round without prioritizing the early bands. So generally it bans sequentially but without any optimal strategy. So for example, in this given example, the radiant R had two options to ban, that is this particular D present at index 1 or this particular index. So it just bans the first available opponent instead of maintaining a strategic turnaround. So it also does not ensure the most effective bans immediately, that is it keeps looping over the entire list. So this results in unnecessary iterations and does not always make the best immediate choice, which is why it is not considered the optimal approach. So now that we have seen that the brute force approach didn't work properly because of few limitations, and we discussed the limitations as well. Now let's move on to our optimal approach, where we are going to use a greedy algorithm with the help of queue-based approach. So this particular approach follows this principle, that is it always bans the earliest possible senator from the opposite party, that to maximize the chance of survival for the current party. And we'll use a queue to track the order of senators efficiently. The sequence of banning the others party is more important. So it ensures that senators vote in the order they appear. And finally, pushing the banned senators is index plus n, that is to represent its next possible voting round, ensuring that we prioritize earlier senators. So this particular approach works because the sooner a party bans its opponent, the higher its survival chances increases. So secondly, using the nearest opponent ensures fewer active enemies in the future rounds, because in our brute force approach we can randomly ban the other's party senator. That is, in this particular example, R can ban this particular D or this particular D or this particular D. So if he bans the second D or the third D, first D can ban the following R and can delay the win of this particular radiant R. So instead of delaying that win, it might also give the alternate chance for this particular current party. So to avoid that, choosing the nearest opponent is the optimal solution. So this greedy approach in our optimal solution will ensure that fewer active enemies will be in our future rounds. And finally, delaying banning decisions, that is random bans, can lead to suboptimal outcomes, that is leaving strong opponents alive longer. So let's quickly dry run with this given example, our optimal approach, how this particular optimal approach works, where we are using queue based approach. So in our optimal approach, we are going to use two queues where we'll store the index of the both parties senators. So one queue would be the radiant queue, which will store the index of all the radiant senators, and second queue would be for the dire party, which will store the indices of all the dire party senators. So in this given example, the radiant party senators are present at index 0 and 3, so we'll store 0 and 3 here. And finally, the dire party senators are present at index 1, 2, and 4. So we'll store the indices of those senators in this given queue. And after storing all the indices of the both the parties, we'll try to compare the indices of both the senators. The person who comes first will ban the next party's senator. So we'll try to compare the indices of both the parties' senators. So the first comparison here would be that is 0 and 1. So since 0 is less than 1, 0 would be banning the 1. That is the party present at index 0 will ban the party member who is sitting at index 1. So the 1 moves out of the queue and we'll try to push this current senator back into the queue for the next round. So we'll add plus the size of this given queue, that is 5. So this current senator with this given index value, that is 0 plus 5, would be pushed back into the queue. So this would be our first elimination. So after doing this first elimination or banning the particular senator, our queue would look like this. That is, the radiant queue have the values 3 and 5, and the dire queue has the values 2 and 4, since one is being eliminated from this queue. So in our second comparison, the values would be 3 and 2. So since 2 is less than 3, the dire senator would ban this particular radiant party R, which is present at index 3. So 3 would be coming out of the queue or getting popped from the queue. And we'll push this current senator for the next round by adding the size of our string, that is 5. So 2 plus 5 is equals to 7. So this current senator would get the value 7 and would be pushed back into the queue for the next round eliminations. And finally, after this second elimination, our queue contains the values 5 and 4 7. That is 5 in radiant queue and 4 7 in dire queue. So again, we'll compare the indices of these two. The person who comes first, or the person whose index value is less than the second party's index, will try to eliminate that person. So since 4 is less than 5, the member from dire party would eliminate the member from radiant party. So 5 would be popped up from the queue, and for the next round, we'll add the size of our Senate string to this particular current dire party value. So 4 plus 5 is equals to 9. So 9 would be pushed back into our queue. So now we can observe that after this third elimination, the radiant queue becomes empty. This particular queue is empty and no radiant party members are present in this next round. We can conclude that the dire party wins, as all the parties from this given dire party has right to vote and they can finally announce the victory. So in this case, the dire party wins. So this would be our base case, where if any of the queue of this given two parties becomes empty, the alternate party becomes the winner. So this would be our optimal approach. So let's quickly code this particular approach and let's finally analyze the space complexity and time complexity. So here's the code for our optimal approach, where we are using queue based approach, which is kind of greedy algorithm, where we are trying to eliminate the nearest possible radiant party with optimal strategy of choosing the next sequential index. So here I've used two queues, that is one for radiant and one for dire. I've iterated over our Senate string and pushed their respective index into their queues. And finally, we'll do this particular process where until or unless any of this particular queue becomes empty, we'll grab the index of both the queues, that is R index and D index, using dot front method, and we'll compare the index to determine who bans whom. So person whose index value is less than the other, he has the right to ban the next person. So if R index is less than D index, so radiant senator would ban the dire senator. So we'll pop the radiant value and dire value as well, and we'll push the radiant value, that is R index plus N, back into the queue. And if D index is less than R index, we'll again pop both the values and we'll push back the dire values, adding plus N into the queue. So we'll do this process until unless any of the queue becomes empty, and we'll finally check if the radiant queue is empty, then we'll return dire as an answer, and if not, we'll return radiant as an answer. So this would be our optimal approach, where we are using queue to store the indices of senators of both the parties, and we'll compare the indices. Based on the value of those indices, we can determine which party will ban the other party. So let's quickly run this code. It's working, so let's submit. As you can see, this works properly. So let me just again explain why we have added plus n here. So generally each senator in the queue represents a turn in voting. So since voting happens in rounds, a senator who survives the current round should be able to vote again in the next round. So but only after all the current round senators have had their turn. For example, if this particular elimination is being happened, so if this particular index has been survived for this elimination, he should also get the chance to eliminate again for the next round. So he need a proper position, or he need the proper way to strategize when he can vote again or when he can ban again. So for that we are using plus n here. We are trying to add plus 5 to reorder the senators in the eliminations. So generally adding plus n ensures that the senator appears in the next round after all the senators from the current round have voted. So generally it preserves the original order while simulating an infinite loop until one party remains. So since the queue naturally sorts based on index order, the earlier index always bans the later one, which ensures fairness by moving surviving senators to the back while keeping them in order for the next round. So this particular trick efficiently simulates rounds without modifying the string, leading to an O of n solution. So generally this approach takes O of n time complexity, and it also takes O of n space complexity. So this would be our time and space complexity of our optimal approach. So let's quickly move on to our time and space complexity analysis of both the approaches we have discussed. So in our brute force approach, the time complexity was O of n square, as we were using a while loop, and for every while loop we were checking the current senator party value, and if the party value is R, then we were again looking for the next available another party value, that is D. So we were using two for loops, and we were checking for every current party. We were trying to find this alternate parties member, and we are trying to ban them. So it took O of n square time complexity, and since we have used a vector of bool to track the current senator party who has the right to vote or not, so the space complexity was O of n. Whereas in our optimal approach, where we have used queue-based approach and sort of greedy algorithm as well, the time complexity of our optimal approach was O of n, as each senator is processed only once. And since we have used two queues, which will store at most n senators, the space complexity remains same, that is O of n. So this would be our time complexity and space complexity analysis. So that's it, guys. We have started with a brute force approach, but it was too slow. Then we have optimized using queues, reducing the time complexity to O of n. So using a greedy strategy, we efficiently predicted which party could win. So if you found this video helpful, don't forget to like, subscribe, comment with your approach to solving this problem. So stay tuned for day 29 of the LeetCode 75 challenge. Until next time, happy coding. Thank you.